last important one. Ah, okay. Yeah, so that happened. So now you will need to reshare the screen.
Yes.
Yeah.
Let's see, share a window.
Sorry for that. It's always.
Yeah, it's okay.
Difficult with that.
Can you see now?
Yes, perfect.
Okay, great.
Seminar on hypergraphs. Okay, so Carlos is going to be a bit late. So if you want, because we don't also want to, of course, make start later than we promised to other people. So maybe what we can do is that I can start already to present you as a speaker, and then afterwards, when people will be joining, they can also maybe watch the recording, the beginning of the recording, then later on. Okay.
Yeah, sounds good.
Yeah. Okay. Great.
Yeah.
So I'm really happy to present you to Phil Chodro, who's a researcher from the Department of Computer Science in the US. And I'm happy that you came to our seminar, because this year we're starting actually with the seminar series, especially focused around the topic of how networks and hypergraph theory can bridge the gap between different theories, including analysis of data and including some statistical validation. So your actually research topic fits perfectly to this series. And the floor is yours. Thanks a lot for coming.
All right. Thank you, Lipa, for that wonderful introduction. Thanks for being here. Thanks for the opportunity to share some work. So as mentioned, my name is Phil Chodro, and I'm coming to you from the Department of Computer Science at Middlebury College in beautiful Middlebury, Vermont. I'm an applied mathematician by training. And I've kind of made a bit of a sideways move in my career into a computer science department, where I'm still continuing to work on some of my favorite topics. What I study mainly, I look at network models and algorithms. I work on some models of dynamics on networks, especially opinion dynamics. Recently, over the last couple of years, I've gotten into some projects related to data science with applications towards social good and social justice. And now I'm a professor at a liberal arts college, and this is a place where we really value teaching. And so I'm also spending a lot of my time now thinking about how to be an effective teacher of undergraduate students. We're a small, primarily undergraduate institution. There are no graduate students in Middlebury, Vermont. And yes, it really does look like this in the picture. It's a beautiful sunny day over here. The mountains are in the background. It's all very nice. It's a nice place to be. So I'm here to talk to you today about some work that I'm doing on hypergraphs. So as we're familiar, a hypergraph is a generalization of a graph in which edges can contain an arbitrary number of nodes, necessarily more than just two. So here's a visualization of a hypergraph made using XGI, which is my personal favorite software for working with hypergraphs. So when I first started thinking about hypergraphs, a lot of the things that I thought about were about kind of generalizations of graph topics. And so if we ask ourselves what's special about hypergraphs, there's a lot of stuff that we can study that isn't necessarily that special about hypergraphs, and I spent a lot of time studying it. So for example, I've thought about community detection on hypergraphs, core periphery on hypergraphs, configuration model of hypergraphs. So I spent some time thinking about, okay, how do I generalize stuff from graphs to hypergraphs? And that's a reasonable thing to do, but I eventually got interested in this question of, hey, if we stop trying to generalize stuff from graphs to hypergraphs, but instead just ask, what's interesting or special about hypergraphs themselves? What are the kinds of qualitatively different things to care about in hypergraphs? Questions we can't even ask for regular dyadic graphs. What's really deeply special about these objects? And so the answer that I'm going to offer you today is two-edge motifs. Two-edge motifs. So what are two-edge motifs? Let's go and visit the space of graphs for a moment. So this is a figure from a paper in 2002 by Milo et al. That really introduced the idea of motifs in networks. So a motif is just the structured subset of edges, in this particular image, a directed graph. And in this setting, we might ask, okay, if I fix a specific motif, how often does it appear? Does it appear with other motifs in some way? How do I interpret? The thing that I just want to point out about these motifs, so there's 13 that are visualized here, and they're all the motifs on 3 nodes when I have directed edges. If you look at these, there's only 3 of these motifs that can be formed with 2 edges alone. All the others require 3 or more edges. And so in some sense, well, this is, I'm going to say, moderately interesting. I'm very constrained in what kinds of motifs can occur using only 3 edges. Furthermore, if I consider the space of undirected graphs and I ask myself, hey, if I'm going to use only 2 edges, what interesting motifs are there? The answer is really there's just 2 possibilities in undirected graphs. If I look at 2 edges, these are really kind of the only 2 things that can happen in an undirected graph. And so I'm quite limited in that way. On the other hand, when I go over to the space of hypergraphs, there's something quite different and quite rich that can happen. Suddenly, when I'm in the space of hypergraphs, I can have diverse, undirected 2-edge motifs. So I can ask myself about the sizes of intersections, and the intersections can be more than just 0 edges or 1 edge. I can consider intersections with 2 or more nodes in them. I can consider intersections between hyperedges of different sizes. So maybe an intersection of size 3 means something different when both hyperedges are of size 4 compared to a case in which one is of size 7 and one of which is of size 20. So suddenly there's this whole rich space of possibilities I can explore. So I can look at 2-edge motifs, ways in which 2 hyperedges can interact or be related to each other in a way that I simply can't in the case of simple undirected graphs. So to put a little structure on this, what I'd like to do for the remainder of this talk is I'm going to assume that in the hypergraphs that we're studying, each edge is going to have a discrete time index. So we can think of this as considering a hypergraph to grow over time in some way, in discrete time in particular. And one of the funny things about this talk is that some of the results I'm going to show you, sometimes the data actually has timestamps that allow us to do this, and other times we actually can assign indices arbitrarily. You just randomly assign time indices to the edges. And surprisingly, this actually works pretty well for some of the models we're going to talk about later. So this might feel like a somewhat restrictive assumption, but it's going to turn out to not be too bad. So one of the things that we can ask ourselves about when we consider hypergraphs with some kind of discrete time index, we can ask ourselves about what I'm going to call the intersection profile. So this is a way to start quantifying the idea that we have rich intersection structure in our hypergraphs. So the intersection profile says, hey, look at the hypergraph at a timestamp t. From all the edges that have arrived up to time t, pick uniformly at random 2 edges that I'll call E and F, and then ask yourself what the size is of the intersection of those edges. And if the size of the intersection is k, then just log that, and we can turn this into a probability distribution. So we can say, okay, this empirical probability distribution, this is a histogram, essentially. It says, okay, the probability of realizing an intersection of size k when picking 2 edges uniformly at random from the hypergraph up to time t. When we measure in this way, we ask ourselves, what's the probability that 2 uniformly random edges will give us an intersection of size k? And we look at some data. Something kind of interesting happens. So here are several data sets in which I've measured this quantity, the probability of an intersection of size k when selecting 2 uniformly random edges, on a variety of data sets. These are data sets that are packaged with the XGI project. And so what I've done is I've measured this over time as the edges arrive. All of these have time-stamped edges, so there's a meaningful sense in the data in which the edges arrive over time. So I've measured over time this intersection profile as edges arrive. And there's something kind of interesting that happens here, which is that if you look at the slopes of these intersection curves as edges arrive, if you look at the slopes tend to not very strongly depend on k, the size of the intersection we're considering. And they tend to be, if you sort of eyeball the slopes here, and I've given you some lines to eyeball the slopes on log axes, the slopes tend to be, around number of edges to the -1 or number of edges to the -2, roughly, somewhere in that range. This is a little bit surprising in that if we considered ourselves to just be generating edges at random, so we were just picking an edge by selecting some nodes uniformly at random from the set of all nodes, if I wanted to create an intersection of size k with another hyperedge, well, that's k independent events that would need to take place in order for that overlap to occur. And so the expected decay rate for that kind of event would be order t to the -k. So what I would expect from this very simple null model would not be what I see in the data. Instead, I would expect to see decay at rate t to the -k. So the slopes would depend very strongly on the size of the intersection I was considering. So this kind of motivates our big idea here, which is that real-world hypergraphs from data, have larger intersections in them. They have large intersections, relatively high values for the probability of intersections of size k for large k, relatively large values that are not easily explainable by heuristic null models. So in other words, large intersections are more common in hypergraphs than would be expected by random chance. So the motivation here, what I am working on doing with my amazing collaborators, is to ask ourselves, hey, what models of growing hypergraphs can generate this large intersection behavior? This is kind of a math modeling question. Then, a bit more of a computer science type question, are these models predictive of future edges? Can I use them for link prediction tasks? And then furthermore, because I'm a mathematician, I want to know, are these models mathematically tractable in some way? Can we analyze them in some interesting fashion, either exactly or approximately? And the answer to the first question is one possible model is the model I'll show you today. The answer to the second question, are these models usefully predictive of future edges, is yes. And the answer to are they mathematically tractable is also yes. So that's what we're going to do today. Mathematically tractable predictive models of growing hypergraphs with large intersections. So this is joint work with two amazing collaborators. So first is Dr. Xie He, who recently completed a PhD at Dartmouth College, now with Microsoft Research, and Peter Mucha in mathematics at Dartmouth College. And broadly, our theme here is mechanistic, interpretable, and learnable models of growing hypergraphs. So if you want to model the idea that some hypergraphs have intersections that are large, another way to say this is that they have many edges that are similar to other edges. And if you imagine this idea over time, then you might say, hey, new edges that get added to a hypergraph are often relatively similar to older edges. And so this is a plot from an amazing paper that I really like by Benson, Kumar, and Tompkins, Sequences of Sets, back from 2018. So they actually looked at the arrival of edges in a hypergraph, and they measured questions like, hey, how many edges are actually exact copies of previous edges in the hypergraph? How many are entirely novel and contain no nodes that have previously existed? How many are perfect subsets? How many are perfect supersets of previously existing edges in the hypergraph? So there's all these repeating patterns that go in. And this has inspired a number of models, really too many models to kind of exhaustively survey, around the general idea that we can form new edges by making noisy copies of old edges. So if I want to add an edge to the hypergraph, I'm going to grab a previous edge in the hypergraph in some way, I'm going to modify it in some way, and that'll be my new edge. And so this is an animating insight behind a number of different kinds of models, and so our model fits into this class. Here's what we're going to do. I have a hypergraph. I want to add some edges to it. So I'm going to consider myself to be in time step t. Okay, so if I want to add a hyperedge to my hypergraph in time step t, what I'm going to do, first I'm going to select an edge uniformly at random from the entire edge set. Then from that edge, what I'm going to do is I'm going to select a number of nodes from that edge. I'm going to do a binomial selection. So I'm just going to, for each node, I'm going to flip a coin with probability of heads alpha, and then ask myself whether I'm going to keep that node or not. The only thing is I'm going to condition on selecting at least one node. So I'm making a small modification here. You can also think of this as always selecting one node deterministically and then doing a binomial selection process for all the rest. So I select an edge uniformly at random, and I select some random number of nodes from it. Then what I do is I add some new nodes, or some nodes from the hypergraph L, some number of nodes from the hypergraph L, so that's in blue, with probability gamma sub L. And then I see that I made a mistake in my slides. I also add a novel node, the purple node here, from outside the hypergraph. So this is a node being added to the hypergraph entirely. So I start with some edges, or one edge. I grab some nodes from it. I take a node from the hypergraph, or one or more nodes from the hypergraph, and then I add one or more nodes from space, essentially, to make the hypergraph larger over time. And with this three ingredients, I can form my hyperedge. So I have 3 sources of nodes that go into my hyperedge. And then this is a single time step. Once I've done that, I'm ready to repeat. I select a new hyperedge and the process begins again. So a little more formally here, what's going on? I have some parameters. So my parameters are alpha, the node retention probability. It describes the number of nodes from an edge that I will retain when I sample from that edge. I have a vector beta. It's a probability vector, and this probability vector describes the novel nodes. So I'm going to add number h of novel nodes with probability beta sub h. And then I'm going to add a number L of nodes from outside the edge, but from elsewhere in the hypergraph already existing, with probability gamma sub L. So these 3 parameters, alpha, beta, and gamma, are my big picture parameters for my model. Beta and gamma, I call them parameters, but really they're vectors of parameters, and they live in the probability space of some maximum dimension k that we need to set in advance. So this is the full parameterization of our model, and we've given a mechanistic update for what you should do in each time step. So if we've done this, we can start asking questions about the structure of this model. So I know I said prediction and mathematical tractability. I'm a mathematician, and so I actually want to do mathematical tractability first, and then we'll talk about prediction a little bit. So what can we say about the structure of this model? What does it do? How can we understand its behavior? So we can start, I want to start with kind of a simple question, which is the mean edge size. What's the mean edge size generated by this model? So to address this question, I want to define just the mu beta and mu gamma. So mu beta is the expected number of novel nodes added in each time step. It's just the mean of the distribution beta. Similarly, mu gamma is the expected number of nodes added from elsewhere in the hypergraph, so it's the mean of the probability distribution gamma. With these things defined, we can calculate the mean edge size. So let's notate the mean edge size mean of k. So here k is the edge size, and so I'm going to consider its expected value. Well, if we ask about the expected size of a new edge, well, when I do my sampling process, I always select one node from the edge I picked. Then I have alpha times, should be k minus 1, sorry. Alpha times k minus 1 nodes that I can select from, plus nu beta plus nu gamma, describing the mean number of nodes added from outside that edge. And if I consider a stationarity condition, again, should be alpha times k minus 1 in this, sorry, but the final expression is correct. If I consider a stationarity condition, the expected size of a new edge must be equal to the current mean edge size. And so that means I can actually solve for the mean edge size in closed form in terms of the parameters alpha, mu beta, and mu gamma. So I can quite directly start analyzing moments of this model using just the mechanistic update. I can already figure out things like the mean edge size. A little bit more interestingly, what can we say about the structure of this model? So the mechanism by which edges are formed in this model, if I just quote what I said a little earlier about how this model works, I'm going to accept each node from E into the new edge F with a probability alpha, conditioning on at least 1. I always add at least 1 node from the edge that I selected into the new edge that I'm generating. Always add at least 1 node from the edge that I selected into the edge that I'm generating. So this implies that at least 1 node in each new edge is selected with probability proportional to its degree, because its probability of being selected is proportional to the number of edges I could have sampled containing that node. Okay, so I have a hypergraph, I'm building it up, and in the way I build it up, nodes are being added to edges with probability proportional to their current degrees. This perhaps sounds very familiar. Proposition. This model has heavy-tailed degree distribution. I used to call this power law, but I think it's not cool to call things power laws anymore. In particular, as t, the number of time steps grows large, the degrees of nodes in the hypergraph h of t converge in distribution to a power law with an exponent that can be described in terms of the model parameters. Remember that here, alpha is the retention rate of the nodes sampled in the edge E, mu beta and mu gamma are the expected number of nodes, novel nodes, and the expected number of nodes from elsewhere in the hypergraph added. And indeed, if we check this on synthetic data, this does indeed work. So the dots are a log bin histogram of degrees from simulations of our model. And then there's an exponent here, zeta, that is calculated using this formula. I guess I should have called it p. That has a slope that matches the synthetic simulation quite well. I want to emphasize that this slope is not estimated from linear regression or any other way from the degree distribution itself. It's just calculated directly from the model parameters. This has some interesting connections to preferential attachment hypergraphs. So my collaborators and I, we weren't really going into this with the idea of creating a preferential attachment hypergraph. We just wanted to do some edge copying. But it turned out that just the mechanism we considered was enough to generate this preferential attachment type structure, as well as the characteristic power law degree distribution. One thing that's pretty interesting is that if you fit this model to data, it actually gives you a new way to estimate approximate exponents for degree distributions. So here's our synthetic fit that I just showed earlier, as well as 3 different data sets, NDC classes, email, enron, tags, ASCII, Ubuntu. So these are our data sets where we fit our model to the data, and I'll say what it means to fit the model to the data shortly. But importantly here, when we do the model fit, we actually get exponent estimates that seem to have some relatively reasonable relationship to the degree distribution themselves. They seem to have a reasonable description of the tails of the degree distribution. I'm not saying that any of these data sets are literally power laws or literally heavy-tailed, but just by fitting the model to data, we can actually calculate analytically exponents that seem to describe these tails reasonably well. And again, importantly, these slopes are not fit to the degree distributions. They're actually what happen when we fit the model to the complete data set and then get the exponents out using that proposition. We can also do other math things. So for example, we can learn about the edge size distribution as well. So it's possible to form a slightly complicated matrix A, which is determined by the model parameters. And from this matrix A, we can actually solve an eigenvalue problem. And the solution to this eigenvalue problem, it tells us the distribution of edge sizes. So on the far left, we have the fit of this predicted or analytical solution in relation to simulation from our model. Then we have the same data sets as before. So it's NDC classes, email, enron, and tags ASCII Ubuntu. Using, again, the fit of the model to the data. And we find that the edge size distribution is replicated somewhat well in each case, not perfectly, but in a way that seems to capture some useful structure in the data. There is even more mathematically that we can do here. So I came to this project with this interest in edge intersections. So how often do edges of certain sizes intersect to form edges, edge intersections of size k? Oh, sorry. So this is also something we can analyze. It gets a bit nastier, but we can do it. So here's the a proposition. There exists some constants that I'll call q sub k, with the property that this edge intersection distribution, RK, the probability of seeing intersection of size k at time t when selecting two edges uniformly at random. There are constants with the property that this probability, it's constant if k is less than or equal to k naught, and here k naught is actually 0. So q0 is constant. And then if I want to look at the probability of seeing intersections larger than 0, 1 or larger, I find that the decay is with t to the -1, where t is the number of edges that I've added. So thinking back to some of our comparisons to empirical data, we saw previously that this decay in empirical data is usually between -2 and -1. It's not scaling with k. Our model actually predicts that the decay is always -1, which is not fully realistic, but it's true that it's independent of k. The q's here come out of the solution to a kind of ugly linear system. And this linear system comes from looking at compartmental equations and then linearizing out small terms that depend inversely on t. So if we look at the predictions of this, so what I've done is I simulated our model for 100,000 time steps and then computed r sub k. So r sub k is the probability that two uniformly random edges have an intersection of size k. So for example, the top line, that's the 0 intersection, so that's the two edges are disjoint. This, of course, is by far the most common scenario. But then we can see all these other slopes going down k equals 1, 2, 3, 4, 5, 6, 7, 8. All these other slopes decay at the same rate with the same slope. And when we solve this linear system that I just showed in the previous slide, this ugly linear system, we can actually predict exactly not only what these slopes are, but also the intercepts themselves. We can actually fully describe the long-run behavior of these scaling curves. So there's lots of fun stuff to analyze in this model. It's relatively rich from a mathematical perspective. One of the reasons that we care about this model, so I only need to see some fun math to care about something, but we also care about this model for predictive purposes. We like to fit it to data, and indeed I've already shown you some experiments in which we fit to data and replicated things like the degree distribution or the edge size distribution. So how do we fit this to data? Of course, we have to do that if we're going to do any kind of prediction. We fit this to data using expectation maximization. So the idea here is that, okay, we want to make predictions from data. That means we need to fit the parameters. Okay, so to fit the parameters, we use expectation maximization. What we do is for each edge in the hypergraph, we form a belief about which prior edge it was sampled from. So this is the probability distribution over all previous edges. Then what we do is we consider the expected complete log likelihood with respect to that belief. So if we have that probability distribution, we can actually estimate the probability of, or the likelihood of all the parameters. We maximize that expected complete log likelihood to get parameter estimates, and we repeat this until convergence. This is this very standard expectation maximization procedure. For larger hypergraphs, we need to do something a little bit different. It becomes computationally prohibitive to do regular expectation maximization. And so we do a stochastic variant in which we sample one edge at a time and then do an expectation maximization update just based on that edge. When we do this on the corpus of data sets packaged with XGI, we do spot some interesting patterns in where these parameters lie. So here on the left, I have, or on the top, I have a visualization of all our parameter fits for a whole bunch of data sets. So on the vertical axis, I think that in a previous version of this plot, we called this parameter eta, but that's alpha, the node retention rate, the likelihood that a node is retained when forming an edge. And then, so that's on both vertical axes, and then on the horizontal axes, I'm looking at mu beta and mu gamma. We divided all these data sets from XGI into 4 classes. So we have social interaction networks, we have co-authorship networks, we have biological networks, and we have information networks that are all color-coded. And then the different symbol shapes tell you which one is which. And there's a few fun patterns that we notice from these fits. So in particular, when we look at the social interaction networks, these social interaction networks have very, very high rates of edge copying. So when I copy an edge, I'm really retaining the overwhelming majority of nodes most of the time. And I'm looking at this clustering of blue social interaction networks at the top of these plots. Most of the social interaction networks are up there. There are smaller, relatively smaller rates of novel nodes and relatively smaller rates of extant nodes as well. The only exception here is if you notice the blue dot down in the bottom right, that's the Congress bills data set from the US legislature. So here there's relatively less copying, partly because the legislatures, we get new ones elected every election season. And so there's not as many opportunities to copy. In this way, it's almost a little bit more like a co-authorship network, which also has turnover. Which are the orange points relatively nearby. So these also kind of have this interesting clustering pattern. So co-authorship networks tend to have a moderate edge copying rate, but have many more novel nodes and extant nodes being added to them. Novel nodes are just totally new to the network, extant nodes being added from previous co-authorships elsewhere in the field, for example. Then we also studied biological and information networks. These seem to be much more scattered. There's not any obvious pattern relating these networks to each other in the same way that there is for the social interaction and co-authorship networks. So once we've fit parameters, we can actually look at prediction tasks. So we did a simple experiment. What we did in this task, we had our model learn parameters on the 20% of training data from three metabolic and organic reaction data sets. And the reason we chose these data sets is that we wanted to benchmark our model against some competitors, against some other models. And these were actually the only data sets we could find that were publicly available and which had been previously published with competing linked prediction models for hypergraphs. If anyone knows of more, please let us know. We'd be very happy to try those as well. So what we did is we learned our model on 20% training data from these 3 biological reaction data sets with edges up to size 5. Just some quick accounting here. Edges up to size 5 means that we need 5 parameters for each of the beta and gamma vectors, and then 1 edge copying probability. So that's going to be 11 parameters in total. So we're playing with an 11 parameter model. And what we did was we compared our 11 parameter model to 2 previously published hypergraph neural networks. So neural network models that were trained to do link prediction on hypergraphs. And each of these models has upwards of 1 million parameters. So we're bringing an 11 parameter model into competition with models that have millions of parameters. And on these data sets, something pretty interesting happens. On 2 out of 3 of the data sets, our model is actually best in class for the link prediction task. So in the first of these data sets, our model is just a little bit better than the LHP, a logical hypergraph link prediction model, and much better than the neural hypergraph link prediction model. In the second data set, our model is substantially better than either one by quite a distance. And the third case, our model is the worst of the 3. So the point here is not that the model is definitely much better than any of these neural networks, but we do find it quite striking that this 11 parameter model is competitive at all with these million parameter hypergraph models. So we think this is a promising sign for mechanistic interpretable, relatively low dimensional models, even in the age of deep learning and neural networks. We do have a lot more link prediction results. They're in big tables that will be published as soon as the archive is out, which will hopefully be soon. And on that note, I think it's a good time for me to wrap up. So just to sum up, this is work inspired by the idea that hypergraphs are locally distinct. They have this interesting local structure that regular dyadic graphs can never have, because they have interesting 2-edge motifs, namely intersections. Furthermore, we can model this idea quite directly and simply with learnable mechanistic models of hypergraph formation that are mathematically tractable and allow us to achieve pretty competitive performance on hypergraph link prediction problems. So we are in really the home stretch of getting this work finalized and on archive. Please look for it soon. I'd like to thank my amazing collaborators, Sheha and Peter Mucha, the US National Science Foundation, and of course you for being here. Thank you very much. I'm happy to take time for some questions if there's some, and otherwise, thanks again.
Thanks a lot. Did you hear me?
Yes.
Yeah, okay, perfect. Because I was asking some questions during the talk, and so I thought that maybe didn't.
I see. Okay, I see a question in chat. I'm sorry, I didn't hear anything during the talk.
It was mostly to understand whether you were calculating. Actually, that was actually one of my first questions to you. Whether when you were showing these distributions, you were doing that, applying that to projections, or if you go back to that slide, actually, or that was not the projection, but how did you calculate the distributions? Because I was not sure.
Yeah. So no projections. We're just defining the degree of a node to be the number of hyperedges that it's an element of. Okay,
but did you also look at the projections? Because I mean, I guess the projections are first kind of ghosts, right, of the structure. They don't have the same. But I wonder about the amount of the information always that one. I mean, did you look at that at the as well, because sometimes people do use that, right? Applying even XGI package, for example.
Yeah, so this is an interesting question. Thank you for raising it. We haven't looked at this. So when we consider the projection, the projected degree, suddenly you're introducing this additional aspect, which is the size of the edge. So it's not just is the node in an edge, but also what's the size of the edge that the node is in. And so I think there's kind of a slightly broader topic here, which is correlation between node degree and edge size. So you can ask yourself, what's the probability that an edge of a certain size contains a node of degree k or something like that? And then that would tell you about the projected degrees. You'd have all the information you need to do things like degree distributions over the projected degrees. This is not something we've done, but I agree that it's pretty interesting.
And my next question was actually about this edge size. So if you go to the next slide, it was exactly that. Kind of, I haven't looked at the paper yet, but I guess that it is there. Could you comment a bit more here on how to read this plots? Because typically, right, this is not the question for graphs, right? Because you don't have that, like everything is of degree, I mean, of the same size. So here in the hypergraphs, I mean, in empirical, I mean, it will depend on where your data comes from, but I guess that the idea is to, when you are, for example, randomizing your hypergraph, is always to keep these h sizes distributions, right? So this is one of the constraints, like in the stochastic block models. Or do I get it wrong?
No, I think that's exactly right.
Okay, so yeah. You're fixing that, and then you're, depending on the distribution which you have, you will probably, it will be easier or harder to achieve this, right?
Yeah. So we're not doing any randomization really. We're just taking the edge size distribution in the data. So we just literally do a histogram where we ask what fraction of edges have size 7, what fraction of edges have size 8. And then we fit the model to these data sets using expectation maximization. So the procedure that I talked about later in the talk. And then from that expectation maximization, you get parameter estimates. And with these parameter estimates, you can form this matrix A. And this matrix A, it's a function of the parameters, and I'm kind of asking you to believe me on that. The formula for the elements of A, I think, is not very interesting. It's just a formula where you essentially just ask yourself, okay, what are the possible ways that I could generate a new edge of size k, and how does that depend on the existing distribution of edge sizes? This gives you a recursive relationship that you can turn into an eigenproblem. So what we're showing in the orange is the distribution of edge sizes from the data itself. And then the dashed line is just this eigenvector that we get from solving this eigenproblem with A based on the parameters.